Okay, today we're going to do the three stages of the development of the group algebra, the whole group algebra. We've talked about in the last lecture just working on the class algebra, or what mathematicians call the center of the algebra, the collection of operators that commute with everything or every linear combination of everything in the group, in the six-dimensional space of group elements in this particular algebra. Three of those elements, the classes or their combinations into projectors, are span the center of this algebra and are the what we call the invariant operators in physics. All commuting is the name that you see there. What we're going to be interested in are the maximal set of mutually commuting operators. That's a quantum mechanical thing. The maximal set of operators that I could diagonalize simultaneously. That's the number that we mentioned just at the end of the last class, the rank of the algebra. And that's something that's not talked about very much in any of the group theory books that I know of for physics or chemistry. But it's really important. And we're going to talk about that and other things. This will be the first time that we use our group theory for some calculation that would really be hard to do any other way. And that is being done right here, where I'll show you how to figure out what kind of splitting you would have in any kind of symmetry that you might encounter for atomic orbitals. Now that's still part of what we call the first stage of the spectral resolution of a group, in this case D3. And that first stage today takes up roughly a third of the lecture. The second stage involves beginning the decomposition of a few of the elements in the center, where now you have a choice. You basically have an infinite number of choices, and that needs to be explained. And that's another thing that is not treated in any that I know of, physical expressions of group theory. And then finally, the third stage is to produce the irreducible representations and be able to solve problems in a very interesting way, because we will be then in control of all possible solutions of a Hamiltonian, of all possible Hamiltonians that have D3 symmetry. The same thing that we were successful in doing for the abelian symmetries. The main part of this, which is, I would say, if somebody says they know group theory in physics, it's usually the first stage. They may have little bits of knowledge for the other two stages, but this is one that we'll cover very closely today, and if you don't learn anything else in this presentation, you definitely want to know of the first stage, because you can do a lot with it. Now, we're going to begin here by reviewing just the ideas of the equivalence classes. That's the three classes of this particular group. The class algebra is three-dimensional, and these classes span that. The Lagrange theorems of class algebra, go through that very quickly, and the projectors that we produced last time, I'll also go through that. Then I want to use that spectral decomposition in the form of a character table, the characters being the traces of the various algebraic elements that we make. And that will then let us do some problems that are very important in spectroscopy, and well, basically the formation of solids and all of this stuff, whether it's electronic, vibronic, magnetic. You can use this same stuff that we're going to develop today. And we'll go over these three numbers again, particularly that one, the rank. Then we'll take on the final stages. Okay, so the idea of the first stage is to take a group multiplication table and boil it down. And by boiling it down, I mean it's assumed you've organized the group table by classes, that is, by elements that look the same with respect to this symmetry. And the 120-degree rotations of this symmetry are equivalent. There's really no physical way to distinguish them. There are 120-degree rotations looking down on the top, and then there's another one that's the same 120 counterclockwise rotation, right-handed location, if you look at it from the bottom. And then there are three 180-degree rotations, and they are all equivalent. The group operators that you have available here can transform any one of these into any one of the others very easily in several different ways. And finally, the unit element will always be in a class by itself in any group. Now, a cyclic group like we were treating before, that is any abelian group, all of the elements are in a class by themselves. It's abelian, so when you do a transformation, T operator T inverse, the T inverse commutes over, cancels the T and leaves you with the same element. So the development of classes is a non-abelian feature. And non-trivial, because you can see the algebra that it makes by looking at the table here. For example, two classes are here, two I classes are there, and so forth. And the one that we're making use of for our spectral decomposition is actually just that particular product right there, followed by that one. So that's what we do when we go to reduce this thing. But before doing that, I want to really quickly go through these numbers again, because they appear in all formulas that we use. The order of the group, a little degree symbol in a subscript position before the group, is a pretty good shorthand for the order. And they're the order of the class, the number of elements in the class, the number of elements in the group. That's just what order means for most algebraic terminology. And we have 6 elements in the group. We actually have 3 elements in the class algebra. And then each of these elements, or I should say each of these subsets, class subsets, have a certain number of elements. Obviously, one is lonely by itself. The 120-degree rotations, there are 2 of them. And finally, the 180, there are 3 of them. So, just to make sure that that is a thing. Now, these classes commute with everything that's here in this group. Everything, and it's every linear combination of everything. So it makes sense to consider when we're talking about a class sum, we really mean the sum of the group operators in that class. That's taking you outside. I didn't mention this last time, but as soon as you do that, you're outside of the mathematical realm of group theory. You're into the realm of algebraic theory or ring theory. This is called a ring by some algebraists. Anytime you can do linear combinations and you're allowed to make sums of the things, or such like. Thinking of it as a vector space, that's a very powerful thing to have.
I think a class is not a group. Am I right?
This thing right here?
Is not a group.
Definitely not, because if I take a product of this thing with itself, I don't get just that, or that. And there's no inverse.
Just we can define a class is a combination of groups element.
That's what they are. You
Is
see.
the definition of class?
Like elements.
Yeah.
Elements that act the same.
Oh,
Yeah.
elements.
Yeah.
In this particular case, we're taking elements that transform into each other by the group. So that means GT of a class, G inverse, is equal to the class. It may shuffle them, the transformation may shuffle them, permute them, but it won't give you anything that isn't inside that class. You see. So that means that this particular sum, or this one, commutes with everything else. And they, of course, commute with each other. The same thing here as here, same thing here as here, you see. Okay, now, this is three things. The question that we're going to be asking eventually is, can I have four things that commute all with each other? That's called mutual commutation. Or maybe I could find 5 things in this group that all commute with each other. And of course, if I found 6 things in here that commute with each other, this would be an abelian group. So somewhere between having 5 and having 3, we know those 3 commute with each other, but maybe there's a possibility, and in fact there is, that I can find 4 things that commute with each other, but not necessarily with the entire group. Okay? That number 4 is the rank of this algebra, and it's an invariant quantity. It's a number that goes with this particular group, and you'll never change it. So that is something we're headed toward, but we don't worry about that right now because we're only interested in the center and its various properties of commutation, including what we call cell symmetry. Okay, the cell symmetry of any element is the number of elements that commute with just it. The cell symmetry of this element has an order of 6. Everybody in the group commutes with the identity. Everybody everywhere, supergroups, whatever, they're going to commute with the identity. Identity doesn't do anything, so it gets to commute mightily. But this right here is kind of interesting. What's the cell symmetry of R? Well, it commutes with itself, so at least it's got one element. But it also commutes with any power of R, including R squared and R cubed. So those 3 elements is a cell symmetry of each of the R's. So the order of the cell symmetry is 3 for R. These guys here, each of those commute with themselves and nobody else in this group, except for one. It commutes with everything. So those guys right there have only 2 elements in their self-symmetry, themselves and the identity. Okay. Now, what's interesting is that the self-symmetry order is the order of the group divided by the order of the class. That's what was proved the last time. This order of a self-symmetry is an integer count of operators G that commute with a particular GK. That's a general self-symmetry statement for any group, but in particular we're interested in D3 now, so we're applying that. So the idea is that that self-symmetry group is doing that transformation of G into a self, and then you can take any other operator that doesn't transform G into itself and have it transform into some other element just to be an element in GK's class. So you can find a GK prime somewhere by doing that, you see. And the idea, of course, is that you can do that with any, you could do this transformation to get this other element maybe several different ways. Whatever the number of cell symmetry operators there are, just glom it onto that GT and it's guaranteed to give you that particular element of the class of GK. And then if that's not enough, if you haven't exhausted the class of GK yet, you might find another operator that does that as well. So there might be several operators that would transform you to some element in the class. And the number of them is given by the number of basically left cosets. All of these guys right here, and I'll just sum this up here, there are as many of those cosets as there are elements in the class. Each one of these G1, G2, GL, they would transform GK into some element in the class. And the number of those right here is the cell symmetry order. It's actually got clipped off there. I can see now that that is not showing there. In any case, that order times this order is the order of the group. That's the main idea. So these things have to multiply up to the order of D3, which is 6. Okay? So those are the Lagrange coset theorems, both of them. In fact, that the left cosets or right coset, you can do it on the right as well, will satisfy this relationship. Okay. Now, the next step here is to get the all-commuting class projectors. We want the projectors in this center that are idempotent and complete north or normal. We know this is possible because we know a minimal equation exists for this particular element, say Ki, the class of the 180-degree rotations that we're designating now by I. Used to call them rho. But that cubic equation is about to come out of this thing. I squared it, and then I cubed it by multiplying another k, so I have to use kr times ki, which is 2ki, okay? So I end up here with, let's see if that's what I want, kr times ki becomes...
order.
Yeah, let's see if this is...
Which side are you hitting in? Ki.
I've got ki here, I got there, and that becomes 9 because this is 6.
Yes.
Okay? So I get 9 ki out of that, and that's a very easy equation to factor. And it's from these factors, that is, if I delete one, I get a projector, delete another, get another projector associated with that root, and then finally one associated with 0 root. And that's what we have here. So there are the expressions of the various k's, kappas. This is an easy one. We know that the identity is going to be the sum of these projectors, whatever they are. So 1, 1, 1, eigenvalues of 1 are there. Then the second one, okay, it's going to involve the square, okay, and it has roots 2 and minus 1. So you see a root 2 and minus 1, and you see the root 2 twice. So that one's a degenerate case. And then finally this one has 3 distinct roots. So it's giving us the complete set of projectors if we just write it out using the formula that we developed when we did the spectral decomposition of the matrix 1, 2, 3, 4. And of course you have to multiply that out to get it. But you can very easily invert that, and here is the all commuting projectors expressed in terms of the all commuting class elements of the center. So this is a spectral resolution of the center of the group algebra. And here it is expressed in terms of group operators, but it's really a combination of classes that we're interested in. And it's those coefficients here divided by the order of the group divided by the dimension that's associated with the degeneracy that we have there. So that's the general character expansion formula, and here's the character table written using the coefficients that are here. Okay? Now, we've got to see what these characters are, particularly these. This is the new one here. This is indicating that a level labeled by this symmetry will be doubly degenerate. That is, the trace of the matrix that goes with this is 2. That means that this projection operator right here still can split. We can split this operator and make 2 out of the 1. So when we're done doing that, and that's the second stage of this group development, when we're done doing that, we will have 1, 2, 3, 4 projection idempotents. And that's the rank of this group algebra, 4, which is the sum of these numbers. Now that's quite mysterious right there, but we'll find ways to prove that as we go through all of this theory in a second pass. We need to do that. That'll be the next lecture, and it'll be a grueling one because we want to really nail down all the little pieces and fine details of this structure. But you can see those numbers, order of class, and then these numbers right here, which are dimensions of a particular alpha representation. And the classes, of course, are labeled 1, R, and I on the top. So this expression of the kappas, the class sums, in terms of the projection operators, these are the formulas for the eigenvalues in terms of the numbers that we're going to be working with. Character, order of class, dimension. In this case, the dimension goes outside with the order of group, and we just have a sum over all of the kappas there, which is the same as the sum over all of the group elements, because these characters are equal for each of the class elements. R and R squared are transformed into each other, and therefore the trace is invariant for any matrix that represents them. Okay, so this is really an important idea. This is the projection resolution of the class algebra, or the center of a thing, and it's general for any group. But it's also can be generalized for any algebra. Algebra that is not identified as a group in the beginning. Okay, now what we'd like to see is how you would spectrally resolve those 6x6 matrices down to what we really are interested in here, the irreps, irreducible representations, the D functions, whose characters we now have, but we need to get the actual representations that they stand for, whose traces they are. So we're going to talk about subgroup splitting when this happens, in this particular thing we call a frequency formula. We need to do that very shortly, but let me just state what's at work here. We're hoping we can spectrally resolve all of these matrices into something. Now we know we can't diagonalize them. They don't commute with each other. They commute with those weird guys that we call the duals. And that's a whole other story. We're just now looking at one particular group of operators, and that's a commuting group that's very useful, but we need to spectrally reduce as far as we can these matrices to the diagonal. So let's look at the representation of one of our projectors. The first one is just a sum of everything divided by 6. That's an idempotent. Multiply that thing up, this matrix right here, and you just get a whole matrix of 6s. So I'm dividing by that 6. You multiply this thing by itself, and you get itself. If I look at the trace of this matrix, well, the trace of it is 6, but trace of 6 1/6 is 1. So that tells you this matrix is only going to diagonalize to a single 1, which I'll just arbitrarily put in the first spot here, and 0 everywhere else. Okay, once you've found the trace, that tells you that's what you're going to get. This is an idempotent. It squares up to 1, so the only thing could be eigenvalue is 1 or 0. And actually, that's what you're seeing here is all zeros except for 1. The other one that came next, what we call A2, its trace also is 1. So let's say if we're going to diagonalize those two together, let's put the 1 for it in the second spot. And the trace of this one is very interesting. Okay? The trace of this is 6 times 2/3. 12 divided by 3. 4. So if I were to just diagonalize that thing by itself, and I can't diagonalize it along with those, but in some basis, this would reduce to 4 ones. It's idempotent. It only has p squared equal p, so it only has 0 and 1 for eigenvalues. And it's got at least 4 ones, exactly 4 ones, and then 2 zeros. Okay, so that's what this one would reduce to if you were just going to diagonalize it by itself. I could make it do that. All right? Now, we got to be a little bit more careful, because we have to say, well, what could we reduce it to in a single basis, make a single basis that would take care of all of these elements here. So the idea is that we could do some sort of transformation of this regular representation to make the regular representation of this particular idempotent look like that, okay? And that would mean then that this particular projector times a group element would look like that, some number. That's an irreducible representation of that particular algebraic element. Now this G could be any element of the group that I've listed here, but also any linear combination of all of the elements of this group. The next part here is just saying, similarly for this one, okay, it would reduce to that. Now, I think I made a little mistake here, because that's true, but if I'm going to get that for that one, then this has to be somewhere else under there, so it should actually be in a little blank space that was left for it there. That is what it would reduce to. And then this one, this is the one that's really interesting. We have to show that it is going to, if I arrange it all right, it's not going to use the space for the A1, it's not going to use the space for the A2, so there's where it should have been. It's going to make little 2x2 representations that have a trace of whatever the character of this thing is times 2. So that's the one thing I want to make a point of here, is that this set here with these 1s and 0s spread all over the place can be crushed to the diagonal that way. There'll be 2 that are exactly on the diagonal, and then there'll be two identical 2x2 matrices also sitting on the diagonal. These are each called the irreducible representations of the group in question here, which is D3. Okay? So this is giving a roadmap of what we would like to produce with this any non-abelian group, but in particular D3. Okay. Now, what we just given the common names for these particular representations. This is called block diagonalization. The idea that all of these things can be block diagonalized all at once by a single transformation. That's really quite magical because they horribly non-commute. The chance of getting them all on the diagonal is 0, but be able to make a simple thing like that is important. And the way to see that is to take the trace of all of these. Well, the only one that has a trace is this one. So all of the, shall we say, the trace power is concentrated in the unit. None of the other elements has any trace at all, right? And that has to do with the fact that no two elements in any group table are repeated. And if the one has taken up the diagonal, then all the other ones have to stay off of the diagonal. So the idea is that we have to make this particular trace using some amount of this plus some amount of this plus some amount of this set of traces. And the idea is that one of these plus one of these plus two of these, okay, 1, 1, and 2 times 2 is 4 is 6, so that gets that number right. And then I have to have 2 times the minus 1 plus 1 plus, that gives 0. And then, well, this is 0 already, so it's just a sum of those two for the last one also gives 0. So this is showing that 2 of these representations that have a trace of 2 for the identity and a minus 1 for this class and a 0 for each element of this class, there will be 2 of them in the reduction. And then these guys are going to be all by themselves. They're not going to have any partners that are like them. And that together accounts for 6 algebraic elements that will match finally onto the 6 group operators. When we do that, we're going to have a spectral decomposition of these elements into 6 not idempotent projectors, but idempotent and then some nilpotent projectors. There's got to be 6 of those things. The catch is that these are unique, but these aren't. There's lots of freedom here to pick different types of irreducible representations. In most groups, that's the thing that really makes the kind of group theory that is present in most of the physics books ugly. It's something that's been left flapping. So we've got to find a way to grab that. If you know about sailing a boat or flying an airplane, you know that if anything starts flapping, that's the beginning of your disaster. Anything is loose, anything is wrong, something put, 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 making a bad sound, you go for it, because if you don't, you have a really good chance of being killed. Now the same thing's in mathematics. You may not get killed, but you'll get stopped. Anytime you have some loose stuff flapping, and that's what these are. These are going to flap like mad. We've got to find a way to nail them. Something's missing from your theory. Okay? That's the philosophy. And that's what is wrong in the present developments of the group theory. Now they managed to work through it because if you have all this extra freedom, you take this path sometimes, you take this path sometimes, and if you haven't tripped, you get a result that works. But how do you catalog all those different paths, you see? We're making a claim here that we can do all possible Hamiltonians of the symmetry, you see, and find all possible eigensolutions. That's going to require having nothing flapping. So that's where we're headed here. Okay. So while this thing will be diagonalizable into the same form, this guy here is not unique. The other two are. There's nothing you can do with them. They're kind of like the abelian groups, one dimension, everything. All right. Now, the idea of taking a group and then looking at the representations that are irreducible for the whole non-commuting group, you might find some subgroups in there that are abelian, and we certainly have nothing but abelian subgroups of this D3. C3 and C2, there are three of the C2s and one C3 group in there. Those are abelian, so if you take a irreducible representation of the whole group, it will not be irreducible with respect to them. So if I consider just a subgroup, a subset, choose a subset, say C2 or C3 of the D3 group representation that was irreducible, it won't be irreducible with respect to CT or C3. It will be diagonalizable, the whole C2 or C3, all three elements of the C3, both of the elements of C2, obviously diagonalizable. Okay? So what we need to do is develop a formula that lets you find out how many of some subgroup's representation A is contained in an irreducible representation of the whole group alpha. That's what we're after eventually here. And then we're going to use that to see what sort of splitting, that's what reduction gives you, of a degeneracy you get, what some multiplet of an atomic level will give you that is labeled by the D3 representations, A1, A2, and E. That's all you've got. They're going to be repeated in some pattern in your splitting. So that's, if we can accomplish that, just that today would be enough, but I'm going to try to do more because it's a beautiful story. I'd like you to see the whole thing once before we go back and work on the details. So what I've just said is that the subgroup splitting involves this, that's a funny name to it, correlation is sometimes the word, correlation or a frequency formula. Do not confuse this with spectral frequency. It's just an integer that's counting how many times did I find this representation A, say 1, 2, 3 times, when I just looked at the element H of the irreducible representation and then proceeded somehow with some kind of matrix, and that involves projection operators, which we will build later, that reduce it as far as it'll go, you see, with that subgroup. And so this number right here, frequency, is, if that were all there were, 3. And then maybe there's some other representation in there that's maybe bigger, so you couldn't have 3, but you might get 2 of them, say. Okay? So it's finding these numbers in the situation where you started with a big group that had lots of symmetry, and then something came along and crushed it, or a magnetic field came along and gave it all kinds of gauge whirl, or something happened, you tore a piece of it off maybe. It is now lesser symmetry, a subgroup symmetry, say H, of an original G, and you like to see how the spectra of that thing degeneracy split. Maybe a 4 would split into 3 and 1, or 2 and 2, or maybe it splits in all four. You see, this is what we want to find out by doing a calculation just with traces, just with characters. So that's the thing we want to do. Derive a formula for the integral correlation subgroup contained in the big group, the global group, say, correlation coefficients, okay, the frequency, the number of times that the little subgroup representations appear in this monster, which is an irreducible representation alpha, that has been treated so that it's as diagonal as it gets for this subgroup. Originally, for itself, it was as diagonal as it gets by being that whole thing filled up. All right, does this make any sense at all? We have to do some examples, obviously, but we can come back and discuss, I think, this if you don't have an explicit equation, or a question, I'm sorry, at this particular moment. The idea that lets me make a formula is cool. Because if that's the situation I have, and I'm interested in a particular projector of the subgroup, okay, that is a projector from the center that would have all ones on its representation. There'd be 1, 1, 1 here and here, but 0, 0, 0, 0, 0, 0, 0, 0 everywhere else in that matrix for all the other ones that we're not looking for at this particular moment. We're asking for this frequency for the greenies, the B's there, okay? Well, that trace, you see, would be the number, the frequency number, in this case 2, times the trace of each of these unit matrices. That is, each of these would be 3, so it would be 6. Frequency of 2, and this particular case has a dimension of 3. L is equal to 3 for this green type representation, okay? And that's just because the representation of its own projector is an L by L unit matrix. 2 of them are here, and that's the 2. Okay, so that's the basis for making a formula for this thing. So the frequency is 1 over the dimension of B times the trace of this irreducible representation alpha. Say this particular one has a dimension here. If this wasn't even here, well, if this was here and there wasn't anything else, I've got a dimension of 2, 4, 6, plus 3 is 9, plus 3 is 12. So this is a 12 by 12 matrix right here. And it's got in it a projection operator, you see, of the B. It gives me 0 here and gives me 3 plus 3 is 6 there. So I'm interested in 1 over L, that trace, and I can use the formula for the projection operator right here. Okay? So I'm taking the trace of this projector. Well, actually I'm taking a trace of this projector right here because it's a subgroup that we're interested in. So I'm dividing by its order, multiplying by its dimension, and using the character of the subgroup to multiply the trace of this element right here. That's the trace of this element, but it's being represented by this huge matrix, 12 by 12 matrix, of the larger group. Okay? So that means I can get this number by just knowing the traces of the subgroup and the trace that goes with the irreducible representation of the whole group, just for elements that are in that subgroup. It's still a symmetry after I tore the system apart or crushed it or something down to this much smaller symmetry, H. that is contained in what was originally a much bigger symmetry. Okay? So I have to put these numbers in the order of what's left of my symmetry, a subgroup symmetry, H. Okay? And this will cancel, so I get a fairly simple formula here that just involves, and this is making use of the, let's see if I've got that right, yes, the trace of this thing right here, that's this character, this class element, okay, is a sum of the order of the class, and all of those things have the same trace. So this is just the order of the class multiplying the character for the particular class K. Okay. So that's the formula we're going to make use of to do an atomic splitting to D3 symmetry. Okay, now we'll come back to that if we have to, and of course we can come back to the projection relations back on page 24 here at any time. But let's go ahead and see an example, and also go over what it is that is going on here. What I like you to imagine is that originally you had an atom that was free. It wasn't part of anything, and there wasn't anything perturbing it. It was just there experiencing a spherical R3 or orthogonal three-dimensional symmetry. And we'll talk a lot about the wave functions that go with that we'll be deriving by using the methods that we're developing right now. But we already know just from our elementary quantum mechanics that if you have an angular momentum L multiplet, like the L equal 4 that we're going to tackle here, you have 2L plus 1 degeneracy in the presence of spherical symmetry. But when you apply various Zeeman field, that means magnetic, and you get Zeeman splitting, or Stark field, named after a terrible Nazi named Thomas Stark, electric fields of various kinds, or more complicatedly, crystal fields that have various high multipolarities that make a symmetry as low as D3. This is quite a breakdown, okay? And you're going to end up with levels here that are characterized by whatever that point symmetry is. Say octahedral is our favorite for many reasons in this laboratory, but whatever. You're going to have things here with the various degeneracies in various orders, and that's what we're going to try to figure out just with what we know so far, which isn't much. So there's the formula. We're going to use it eventually, but I would like to show you how you get by without the formula if the problems aren't too hairy. And then we'll use the formula just to check it. But let's start with some simpler situations. Now, what it says here is L equals 0 is called an S singlet. Now the S doesn't stand for singlet, unfortunately. S stands for sharp, because the S transitions in hydrogen turned out in a particular experiment to be sharper than others, so they got that name. But the brightest of them were due to an angular momentum 1, L equal 1. 2L plus 1 is 3. That's the P triplet. P stands for principal. Because they were brighter and made good standards, they were called the principal lines, the P lines. Next in line after this is 2L plus 1 equals 3. That's what it is as a triplet. The next one after that, L equal 2, is known as the D quintet. It's got 5 levels in it, okay? That's 2 times 2 plus 1. 2L plus 1 is the degeneracy of an arbitrary L level, okay? D might stand for damn or something like that, because it was a hard level to see. It was quite hard to see. It was diffuse. the D stands for diffuse in the early spectroscopy. It goes back to Fraunhofer, before they even knew it was making these lines. Okay? So that's a quintet. They didn't know that, but we do. 3, whoa! These were really hard to see, these lines in the spectrum, particular spectrum of hydrogen. F stands for fine, but what we know now is that each of those levels has a degeneracy of 7. 2L plus 1, 2 times 3 plus 1. Okay? Well, after that, they label these things alphabetically. What does G stand for? We're able to see G lines. It's a nonette, a 9 degenerate orbit. Lots and lots of degeneracy. Okay. All I can figure out is G stands for God knows. Okay, and H, I guess hell knows. G, H, I, J, K. They just keep using letters. Sometimes they skip J because J is so common as a symbol for angular momentum, so they didn't want to get completely screwed up. But these are very ancient letters. And in molecular physics we go sigma, pi, delta, phi, gamma, and why? See, this is where group theory really helps, because we have much better ways to label them. But that's the standard way of labeling by this ancient spectroscopic terminology. Okay, so what we're gonna take on the L equal 4. Okay, but before we do the formula, and you really need the formula starting about 3 or 4, we'll see what it is that we need to do. Now let me remind you that this splitting right here of levels is mathematically isomorphic to a projection operator, PL, splitting into sub-idempotents that are associated with each of these levels. And by splitting, you know what I mean. A projection operator can be a great big matrix, and it can split into a bunch of little projection operators on the block diagonal. So when you talk about a finite symmetry that has taken an irreducible representation and made it reducible, that's what you mean by splitting. You mean that this alpha level is going to be described by a representation that matches its degeneracy, which I've indicated as 1 here, so there'd just be a number there. Then a doublet, say, might show up here. There'd be a 2 by 2 matrix there. And here's a triplet. There might be a 3 by 3 matrix next. We need to find out which of those alpha, beta, gammas came out of this particular L. So we're going to try L equal 4 and see if that's right. Those are the representations that I think we get. We'll see anyway. Okay? And we're going to do it with characters. From lecture 12.6, page 103. Now, we went through this pretty quickly, so I'm going to stick it at the end of this lecture when we put it up on the web. Just remembered I've forgotten to stick it. It's not on there right now. But just to make it convenient so you don't have to go back and look at that, the derivation of this formula and its geometry was quite beautiful, and I didn't make a big fuss about it when we did it. But in any case, it's the formula that gives a diffraction peak. That's what this is. This is a spectral function of this variable right here, which is an angle variable. Okay? And we're interested in just the angles that are appropriate for this subgroup symmetry D3 that we're working with. Okay? So we're going to use this formula to write the values for the traces, that's the characters, of the unit element, that's angle 0. Okay? Well, that's just 2L plus 1. Okay? 2L plus 1 is 1, 3, 5, 7, 9. That's the multiplets of the orbital levels of a molecule or an atom. Okay? That's easy. But this formula would give you that. It's kind of doesn't look like it at first, but if you use a L'Hopital's rule, you'll see a 2L plus 1 come out of that, or that. Okay? But the next ones, for example, for 2 pi over 3, or 3 pi over 3, that's all we've got in D3, so it's pretty easy. Okay? Try pi, that's real easy, gives you 1 minus 1, 1 minus 1, 1 minus 1. This is a twofold symmetry. It's going to oscillate back and forth over two things. Now this one you work it out with 2 pi over 3, you'll go 1, 0, minus 1, 1, 0, minus 1, 1, 0, minus 1, forever. So I can tell you these characters as long as you want to talk about it. All right? Now the idea is we want to match these traces of the unit operator, the little r in D3, and the i's. So I want to match this with this, this with this, and this with this. I want to make combinations of these that give these numbers. That's the character analysis. If somebody says they know group theory and chemistry uses, this is what they can do. So I'm showing you that right now. They learn how to do that. Now, it's easy if you start with L equals 0. L equals 0 is clearly just A1. End of story. A single one of them. But what about this one? Okay? How did I get that? All right? How do I know that the triplet is going to split into, forget the 0 here, it's going to split into A2 plus E1. It's going to get one A2 and one E1. That makes 3, all right. This is a doublet and that's a singlet. So it's telling me that the triplet's going to split like that. Or maybe like that. Or can't do that because something's got to stay degenerate. Okay? How do I get that? Okay? I notice that if I add none of that to one of those and one of those, I get 3. Let me see if I got that right. I get 3, 0. This should be a 0. Okay, and it is. And then minus 1. Okay? So that's sort of trial and error. I knew I had to add at least 2 of something here, if it was up here, or one of those, to make up part of 3. Just looking at the first column. So the question was it 2 of that and 1 of those? No, that wouldn't work. It could be 1 of those and 1 of those. That would work. But it could also be 1 of those, because that's got a 1 in it, right? That doesn't work. So there aren't very many possibilities now. I can get this pretty quick. Okay? And there's the answer. Okay, that's the splitting of a singlet and a doublet for angular momentum 1. Angular momentum 2, a little hard. It's got 5 things, right? So how am I going to make a 5 minus 1, 1 using these things, you see? Well, I can make a 5 by... if I added those 2 to get out of 4, so I've got to have 2 of something here. But maybe it's 5 of this and none of that. That obviously isn't working. And so forth. You see the number of possibilities goes up, but it's still manageable. And if you work on it, you just say, I don't want any of that, and I want 2 of that and 1 of those, and it works. So that's what tells you right away I got 2 doublets and 1 of the A1 singlets, not the pseudoscalar. I got a scalar. You see how this works? Yeah. And 3 is about the limit where your patience starts to run out unless you hit it right away. Now, there's some people that can sort of, I'm sure there are idiot savants at group theory that could just do any angular momentum. I don't know. But it would be hard, okay? Here, for example, I take 2 of these and 2 of these and an A1. And I get 7, 1 minus 1, which is the answer. So that's what I'm going to have. I'm going to have 2 doublets again, 1 singlet again, but this time I'm going to get 2 pseudoscalars, the A2s. Okay? Well, we really need a formula starting now. If I go for L equal 4, I've got a lot of possibilities. And L equal 4 demands a 9 here, a 0 here, and a 1 there. Okay? See the answer? I certainly wouldn't. So let's go ahead and I've cleared a space here. Let's do the calculation. Okay? I'm first going to start with E1. How many? Those are the big guys. Okay, they double. Okay? So I'm going to stick in the characters E1. I'm going to be using these numbers here, the green numbers. Now this particular formula demands a complex conjugate here, but we don't have to worry about that. Most of our times we're working with real numbers, so that's not a big issue. But when it is an issue, that's where your mistakes are likely to come. So don't forget to count the star for groups like C3 or any of the cyclic groups that has mostly complex, wavy, current representations. So I'm going to stick in here the 0 guy, the 120 rotational class, minus 1, and a 0 for the 180 degree class. Okay, and then I've got to just stick in the orders of the classes. That's 1 because it's the identity by himself. This is 120 degree rotations. There were 2 of those. And the characters from here. 9 goes here. That's the dimension of this multiplet. 9 levels in there. The hiding. Then here is 0. Okay. And here is this last number, 1. Okay? So we just have to add this up and divide by 6. Okay? 3. That's the answer. Okay? Well, we're not done yet. Got to get the A2s. Okay? We don't change anything except the group number. Go for 1, 1, minus 1 now. 1, 1, minus 1. Works out to 1. Okay? And finally, the scalar. This time I put all 1s. And that gives me 2. Okay? So I get 2 of these, 1 of these, and 3 of those. Now, what order? That's a good question. Could be any order at this point. But I want to mention some things that we discovered that very often you can tell what the order is pretty easily. It's roughly that most of the time. I'll explain why later on. Anyway, here are some more. Okay, if I go for 5, I'm going to pick up 4 doublets and 2 singlets and a partridge in a pear tree. Okay? Here's a look all the way up to 6. Just to, see what it looks like. And there's 7. 7 has 5 of those doublets. Now here's what you're going to see if we work this out with a typical simulation. What you're going to see is repeated A1, E1, E1, and I'm putting 1s on these because they do belong to angular momentum 1. We showed that early on. Okay. And then you're going to see an A2. This is sort of a band boundary right here. And then you're going to see 2 more E's, and then you're going to see top of the second band, and then it's going to start with whatever's next. So that's pretty much the ordering that you're going to see for the evens. This is setting the trend for the odds. The odds start out one, then they put the A2 next to the A2 instead of next to the A1 and continue. And then they have two A1s again. So the patterns for the evens and odds are different, but they do have a band structure to them, which we're going to explore later on. That's something that's not seen by character theory. We need to do the full group theory with all the duality and all that kind of stuff in order to make sense out of that. But I just wanted you to know that we've got this under control to the point where there isn't very much that's flapping. However, if you just do character theory the way they usually do it, you leave a lot of flapping stuff. Okay, now, one of the things we should do is just say one more time what the major numbers are that get us an idea of what's going to happen with these group reductions. And the characters have dimensions in the first column. That's traditional. I'm following that tradition. And then they have the coefficients of the projectors have the order of the group divided by the dimension of that particular row as the normalization factors, if you would like to call the denominator that goes with the projection idempotent coefficients. Okay, so just looking with this column, we have the dimensions 1, 1, 2. And to the 0th power, they give us the number of classes. That's the number of classes. I call it the number of invariants, the number of irreducible representation types, the number of all commuting operators. So this number takes care of a lot of subtle things about commutation that occur in this algebra. Now this is my name. I don't have a name really for this that I can find in the literature, but let's just call it the centrum, order of the center. There are 3 dimensions in there, 3 independent things that commute with everything. This is the magic number, rank, and that is in the literature somewhat. Not given enough press, I think. Anyway, the first power sum is a number of irreducible idempotents that are going to split out when we try to split these things individually into idempotents. That's going to make 4 things, which we're going to play with. And you'll see how that finally gets 6 things. But that's a very important number to know. And it's just a sum of the dimensions. That's, as we're going to see when we go through this next time, very much obvious if you look at it right. And then finally there's the square. The square of those dimensions sums up. This is a Diophantine, I think, equation. Okay? And that's got to sum up to the order of the group. Okay? Order of the group. Sum of the dimensions squared. Total number of irreducible projectors, and I mean all of them, the non-diagonal ones, which are nilpotents, and the diagonal ones, which are the idempotents that make up the maximally commuting set of observables. And then these are operators that make transitions. They're nilpotent. And it's the total number of symmetry operators that makes the whole dimension of the algebra, is this last number. Okay. Well, let's go for it. We have enough time, I think, to at least make some progress in what we call the second stage of the spectral decomposition. Okay. Now, this is going to be where we split class projectors. Only one of them is going to split. We know which one that is. It's the E, the one with 2 dimensions. But you can split it a number of different ways. You can split it using a C2 subgroup, and you'll get a standing wave. And you remember what we like to use red colors for stopped waves, standing waves. So that's what I'll do a lot here. But if you want to use C3, then you're going to get a moving wave, something that can go, as in a green light, traffic light coloring we're doing. Okay? And while we're doing this splitting of the all commuting projectors, we're also going to split classes because they have to match. There has to be a linear combination between the class sums that result and the projectors that result. That's a good accounting check for this. So let's go back to the group zoo, in particular the group zoo for non-abelian things, which is what we're talking about here. And D3 is a prime example, the smallest example in the entire group universe that is non-abelian. But it has subgroups C3 and C2. That's what these lines indicate. And it's these lines that tell us all of the different ways that I can adjust the projection operators that split out from the all-commuting ones. The all-commuting ones are invariant, but the last splitting is not going to be invariant. I can choose this subgroup right here, and that's what we'll do first. Then we'll choose this one, C3. Okay, and that'll give us a very different result than this one. So here's what we have to do. If we're going to use C2, that's a choice, that's an uber choice, but there's a sub-choice. Which of the C3s do I want to use? Who am I going to quantize? This is very much like the thing that happens in angular momentum theory, if you know. I can quantize angular momentum with respect to, and it's usually done, the z-axis. But I could quantize with the x, or the y, or something that's somewhere else. I could put my Stokes vector any direction, okay? So you have a lot of choices. That's the flapping, okay? So we have 3 flaps here that we can pick. Besides the choice of whether I do C2 of the I class or C3 of the R class, that's what's going to happen in here. But let's just do the C2 right now, okay? So we look at this character table for C2. Now it's a character table and idempotent table as well. I've got a 1/2 in there, so that's an idempotent operator. These are the coefficients of the elements. And then here's the projection operators, all commuting projection operators from our D3 class sums, which are here, here, and here. All right? So I can see that if I just look at, say, this number and this number, that I see right away that the P0 is like that. And then I see that this one right here, okay, I see a 1 and a -1, so I know that the PA2 is like the P12 as far as these elements go. You see, forget that one in the middle. We'll worry about it over here. Okay, now it'll be a whole different problem. But this one right here, how do I make this? 2, 0? How do I make a character 2, 0 out of those two? Add them up. Okay? 2, 0. So that's what this is going to split into. It's going to split into that thing and that thing. That's maybe a little obvious, actually, when you think about it. It's a vector. That's what vectors like to do in the xy plane. Okay? So here's our correlation table between the symmetries that are associated with, and representations, C2 and D3. These are frequency numbers. How much, when I split A1, how much of this one do I get and how much of this one do I get? Well, I get just that one and none of that one, okay? This is just the opposite. It gets one of the anti-symmetric and none of the symmetric. 0 mod 2 and 1 mod 2, remember? Okay? But this one gets one of each. Okay? All right. So this is telling us just exactly how to make the irreducible projection operators out of this thing. This thing is not irreducible. These are. We've seen that they only split into one of a particular kind. But this one is splitting into two pieces. And that's got to be true, because we've got to get 4 projectors out of this. That's the rank of this algebra. So the rank 4 implies there'll be exactly 4 C2 friendly projections. And so what I do is I take each of the p's that I have here, p alphas for the big group, and I multiply them. This is the 1 equals 1 times 1 trick, sort of, okay? That'd be p alpha times 1, and 1 is p0 plus p1, okay? So I get these 2 projectors by doing that. And I label them with a double index, and we'll see why that is shortly, because we're going to be making matrices, irreducible matrices, out of these things. Okay? So that's the idea. And then, while you're at it, you might as well do the notation with the double indices for the other 2, just using the correlation table. So PE is going to split into a thing like that and that. That's basically what I have there. Okay? But this one's only going to split into that, and this one's only going to split into that. So you turn your correlation table for your subgroup into a projection formula. That's the trick that works so nicely here. And then you work it out. You see what you get when you multiply by P0 and get something that's not 0. If you multiply this by P1, you'll get 0. And if you multiply this one, I'm sorry, if you multiply this one by P2 instead of P02 instead of works, but P12 would not work for this one. It would give 0, so I didn't bother with it because I saw there was a 0 there. And then this one I've got to use P12. Okay, so I use 1 minus I3, and I get this. Those are irreducible projectors for the group D3. They're invariant. They're not floppable. But these are flappable because I can take linear combinations of them and still get a projector. Okay, but one of them is the 0,2 guy. That's what we're going to call PE with a 002 underneath it. Okay, and then this one right here, after I get done multiplying this thing, I'm going to get this right here. So that's a little bit of algebra right there that you have to do. But that gives you the projector. So here are 4 orthogonal projectors that will take care of this whole group. They are the only 4 idempotents, that irreducible idempotents, that satisfy this local symmetry. Let's go for the C3. Okay? We've worked with this one already. We need to look at this one. Moving wave. Okay? Now this time there really isn't much of a choice. There's only 2 of these guys, and they're both really the same. They're conjugates. Okay? So I'm going to take this projection formula for the C3, which we worked on, and remember what epsilon is. It's e to the minus 2 pi I over 3, and then epsilon star has plus sign, right? So I use that, okay, to build a set of projectors. I first draw the correlation table. I can look at this thing and see right away by just looking at the R there, what you've got, okay, is that I've got A1 is just 0,3. A2, what's it got to offer? Okay, A2 over here, well, it's just 1, it's the same. Okay, it's also 0,3. Okay, and then E, how do I make 2 minus 1, 0 out of those things? Well, it's one of it's one of the one and one of the other, one of this and one of that. Epsilon plus epsilon star and epsilon star plus epsilon will give you that. Okay?
The 2 in the bottom of the upper table, is that not a 1?
The 2 in the upper part of the
You have your finger, raise your finger 5 inches.
This way?
Straight up. Okay, the top table projector 2 sub 3, the first index, is that a 1 or a 2?
Oh, yes, just the three. That is a
Small
one.
thing, but type.
Make a note of that. Yeah, that is definitely a typo.
Now when you do your sum,
Yeah,
2 0.
that's right. Yeah.
It's 30.
Thank you. We got that.
It's
That's-
checks.
yeah.
checks.
Slowly but surely, we chase the typos. I often think that manuscripts have an infinite number of typos. Because years go by, oh, get that one, oh, that one. You know there isn't, but it seems that way. Okay, now, rank 4 implies we got a 4, all right? 4 projectors, C3 friendly projectors. We're going to be doing things like that, but the multiplication, you see, is only going to be 1 for that one, 1 for that one, and 2 for that one. And so the projectors that we get in this case will look like this. These are the same, okay? A2, A1. They're both being multiplied by O3, so they don't change at all, except they expand out there. And these are very different. These are real, those are complex. Okay, so that's these are two archetypical choices for subgroup symmetry. And we should notice that when you write them out, the class is split. For these, I call this a subclass for this thing, and then I call this one another subclass. It comes out of the thing, and it's this one plus 2 times that one that makes up what I would have called a single D3 class. So this particular C2 splitting gives you that, but this one is weird. It just pulls out, it breaks R1 and R2 into separate classes. That's a splitting that occurs, and then same thing there. Okay, so that's an interesting aside, but that's just bookkeeping. You make sure that it's happening on both sides of the equation. I have to have 4 subclasses to go with the 4 irreducible, I should say I have 4 irreducible classes to go with 4 irreducible projectors, idempotent projectors. Okay. Now, the consequence of this is that the parameters that I have for D3, which were quite numerous before, have been reduced. If I'm going to have this local symmetry, I have I3 as a free parameter, whereas over here R1 and R2 are the free parameters. You can adjust the amount of circularity. This one is adjusting the strength of the standing splittings. R equal R2 must equal R1. The coefficient of R, the first power, has to be equal to the coefficient of R, the second power. That rules out complex numbers. I has to be equal to I2 and I1. Those two have to be equal to have that. So that restricts the tunneling diagram considerably. And there are going to be 4 parameters in either case. And we'll see what that leads to. Okay, now here's the big kahuna. I'm seeing now that we are a little late. I forget when we started, so.
20 minutes.
What's that?
20
We have
minutes.
5 to go.
We got 5 minutes. That'll be just enough to at least show what the what comes out of this, and then we're going to be really tackling it next Tuesday for the lecture 16.
Bridge yourself.
But this is the centrum, 3 idempotents. There's the idempotents expressed in terms of the classes, and this is what we get now that we've found a maximum number of commuting idempotents, mutually commuting idempotents. These idempotents commute with everything. They're all commuting and totally invariant. Nothing flapping here, but we only have 3 things. We've got a group of order 6. So we've got to come up with 6 things. And we're on our way here. We've got 4. We need 2 more. 2 more things if we're going to go the C2 way. That's the thing that we're after here. So we're going to use the old group element. And we have 6 group elements that are going to expand into 6 things. We're going to use the old G equals 1 times G times 1 trick. Okay, there it is, 1 times G times 1. Where 1, of course, is the sum of all of the 4 irreducible projectors. So there's 1, and there's 1 again. Okay? Looks like we're going to get more than we need. We only need 2 more, but I'm going to have here 16 terms. Or am I? Well, no, you're not going to have 16. Lots of zeros. Why are they 0? For example, why didn't I get something when this thing went through the G to hit that one? Well, that one's all commuting. So it'll commute right through the G and hit this one and 0 it. These are all orthogonal. Guaranteed. And so are these. Okay? But that doesn't explain too much for these guys right here. They are all commuting. Right? So they make a logjam. There's your 4 operators right there. This is obvious, these 2. That makes 6. That's the way you get 6. Okay? So this is the 3rd and final step in the spectral resolution of this group. And it's been made unique by choosing the subgroup. Now, when you actually work these out, and that's something we'll do next time, you will see that this is a coefficient times an irreducible projector. Now this is pretty obvious when they commute. They had to do that. But that's just like the abelian groups. You have a single one-dimensional representation coefficient for the particular group of where you're multiplying the projector. These are more subtle. And you see we have cross terms, xy, okay, along with the diagonal ones, yy and xx. Here's another off-diagonal one that's sitting here, and there's another one here. But these guys that are right on the diagonal of this array of sums are idempotents. These are nilpotents. So you get 2 nilpotents and 4 idempotents that we started with after we did stage 1. I said stage 2 of splitting right here. This is the 3rd stage that breaks it to what we're ultimately going to want. So it's going to be a linear combination of 1, 2, 3, 4 idempotents plus 1, 2 nilpotent operators that multiply off-diagonal components of what we call the irreducible representations. These D's are the things we need to derive. It turns out it's much easier to derive those by just using sines and cosines of 120 degrees minus a sine and then a cosine of 120 gives you that number, those numbers, and then this is just the inverse of that. And then this is done the same way with x's and y's being flipped over on the 1 axis and around the 2 axis. And finally the 3 axis, if you lay it right down on the x-axis, you're going to get the y thing to be minus and the x one to be plus. So those numbers are actually very easy to derive by elementary means. But I will show you next time how you would go about if you didn't have the insight that was needed to realize that that's what those coefficients really have to be to accomplish this particular spectral decomposition of every group element in D3, all 6 of them in terms of the 6 projectors, 2 of which, the last 2 here, are nilpotents, off diagonal, and the other 4 are idempotents that I'm listing here. I'm listing the vectors that go with them in the 6-dimensional group space, and that's what we're really after, because that are the eigenfunctions of this D3 system. I should say they're in the position to become eigenfunctions in the case of the degenerate case. And here's what they look like. Here is the state YY highest. Here is the state A1XX, the lowest. Okay? And even if you are a idempotent that's got no partners, you still want to use the double index when you're being very careful about writing your wave functions. So I use not just one x but two x's here, because what I am doing is tracking the two symmetries. Global symmetry and local symmetry is automatically being done. Here is the Mach-Mach principle being applied. This one is obvious. If I apply an I3 to this thing, we picked it as something to be diagonal, so I'll get a number, and it's just -1 to whether this is even or odd. X is even, Y is odd. That's the designation that I've used here. X is even to I, because I just rotates, or this mirror plane goes through it. It was C3V, so it doesn't change. But the Y is odd, because when you do that I3 operator, it flips to minus. And you can see the little waves that are sitting in the local region here. There's a very symmetric wave function, plus wave, sitting right on the I3 axis, the global I3 axis. And then we also have in the X, the red thing here, is the local symmetry, okay, the body symmetry. The local G, you see, that you're testing it with, will commute through the projectors, you see, and come to the right-hand side, and then give a number according to what that quantum number is right there. And it'll be -1 to whether that's B is odd or even. It'll be minus if it's odd. So you have a local symmetry automatically given to you that tells you whether you have a situation like this, where the local quantum number is odd. Every one of these is odd, you see. And whereas down here, if I look at this one, for example, or this one, you see that every one of these things has an even C2 local symmetry. Here's an odd again. You see why. Okay, so this one, and this one, that's trivially so, it's odd globally and locally. Okay? Here's another one that's odd globally and locally. Now, what do we mean globally anti-symmetric? We mean if we put the plane through there, or the axis through there, and flip it, I get minus everywhere. This plus goes to that minus, this minus goes to that plus through that line right there. That's the global anti-symmetry. Here, if I do that thing, it's globally symmetric. The plus goes to a plus, minus goes to a minus. Okay? Same thing here. Minus minus goes to minus minus. Plus goes to plus. But this one is globally anti-symmetric. Plus plus goes to minus minus. And this one is both globally and locally contradictory, so nothing shows up there. Same with this one. That's a selection rule. Internal global local selection rule. Something that I don't think anybody really understands. That's a very powerful thing right there. Okay? So this is what the waves actually look like, and I want to make sure that you understand the external lab label is the one that will face you when you hit it on this side, but this one is the one that will show up if you hit it with something that could fall through to the other side and give you a quantum number that way. And that's the Mach-Mach principle allowing that. Here's an example of global X symmetry where I don't have any local symmetry at all. It's completely broken. Okay? You just look at each one of these local wells. Well, that one has to be because it's global symmetric, but this one doesn't. Okay? So it doesn't have a local symmetry. This one doesn't have any global symmetry, but its local symmetry is just fine. Okay? An example. Okay? Here's one where the global symmetry is okay and the local symmetry is okay. That's what we were looking at before. So this is what you get by doing the Mach-Mach principle. This is what you get by doing the duality. That's before you've calculated anything. Then when it comes time to look at the eigenstates, or the complete Hamiltonian, using all the parameters if you want. But if you use the particular parameters that are appropriate for this, if you use the local symmetry, then you'll notice that the off-diagonal parts go to 0. So you get your eigenvalue formula straight away with no calculation beyond what we've already done, which is considerable because we're learning this for the first time. Okay? So that's really important. Now here's a simulation, which we don't have time to look at, but there's the XX that goes with this. There are the two XX and YX locally symmetric waves with a very little wave there, but it's not zero because this thing isn't quite obeying this local symmetry. And this one is showing zero there, except it's not. This one's disobeying more because it's close to the top and it's getting ready to get out of this jail. Okay? But it's anti-symmetric locally. And here it can't be globally symmetric and locally anti-symmetric, you see. So it's suppressed. And then this one is really suppressed because it's deep down and it's really feeling the locality. And then finally, this thing is both anti-symmetric with respect to global reflection through my hand, and it is locally anti-symmetric as well. You see, so that corresponds to this one. And as I say, there's a clash here, there's a clash there, which corresponds to the zeros that would be here in the ideal local symmetry. Okay, and that's about it. We're going to also discuss vibrations using this, and there is a typical local limit for the vibrations, and we'll show using TC's program version of Malvives next time, but we'll also come and do some animations of some other possibilities. This is one that doesn't respect local symmetry. This arrangement of springs does respect local symmetry. That gives a very different combination of these modes to satisfy the different local model. This is a very local model for C2. Okay, I'll call it quits there, and if we have a little bit of time left, we can leave it on to answer questions if there are any. It's you pass on the question department. That's fine.
Can I try a regurgitation?
This is a big collection of information that's just been disgorged here, and it's information that has a lot of new stuff in it. So it's you know, you're joining a very small club, but the club will get bigger because in order to do real analysis of things like graphene, you're not going to be able to play the old game. And you can see it. They aren't doing the whole job. There's plenty to do that they're not doing. So we want to take advantage of that. And we want to take advantage of it for all the groups. And I mean all the way up to Poincare, Lorentz. We really want to make use of this. We want to see what relativity of the grand relativity tells us in you know, high symmetry situations.
Can I kind of almost like try a regurgitation?
Yes.
And then maybe we can polish it if it's off.
Okay.
Okay, so we have this case here where we know that there is a degeneracy in this system.
In the spectrum of the system, you're saying?
What's more, we know how...
More than one degeneracy in this particular case.
Okay, we have an E.
Oh,
We know that it's a two-dimensional degeneracy.
that would be true for not just this system, but any system that had D3 symmetry.
It had a 2 in that first column of your
Because of
character
the 2 in the first column of the character table.
Okay, all right. So let me push it a little
Yeah.
bit further. So now we have that. Now, just like in propagating light, you have two polarizations. That's a degeneracy. And so one
It
thing
is a
you do-
degeneracy if you don't put something on there to make the two directions different.
That's it. That's
Yes.
one of the first things we do. We
Yeah.
orient it with the lab or orient it with ourselves,
Yes.
and then use that as a reference to choose one and then the other, which has to be orthogonal to it.
Right.
So then we got it locked down. So the trick you're employing here is what can we use for a frame of reference in that system, but why not some of its own internal symmetry?
Yes, it's an own internal structure, because the system is only there because the wave, which is the thing that's feeling the locality, the actual victim of the potential, if you will, or whatever the laboratory feels like it wants to do to it, okay, tickle it, or crush it, or whatever. The laboratory is the thing that we're very familiar with. What we're not familiar with, and that's what we need to really talk about next time, is how do you put a set of operators on the object, let it do transformations of the laboratory. That's the other side of the group theory. That's the local symmetry group. You see.
So you're using it as a bridge into the body.
Well, mainly we're trying to study the interaction. And the idea is that the interaction, you see, is not necessarily invariant to doing things like that. But no matter what state this thing is in, it is invariant to the whole thing doing something together. And we're ignoring that. We're saying you can ignore that now. And that's what makes it possible for me to say that all that matters is the relative position. This is a very esoteric way to say of the old saw, which is everything's relative. With regard to this system, that's true. Now later on you say, oh, but if I do this, it's rotating, it's got angular momentum total, I've got to worry about that, and now I'm going to put another thing around that, and this will be the system inside, you see. But this system has probably more to say about that than it does to say about that. So we work that out first, and then we can play it again, or this whole thing will be the inside, and there'll be a bigger outside. And so you're always pushing the border between the inside and the outside in quantum mechanics. The inside of the thing is the part of the system which you claim you're going to have accounting for all of the phases. You're not going to let the phases go random on you. You're going to account for them. Okay? So that's the inside, you see. In a situation where you have a potential here attached to its Phillips screws to a heavy lab bench, you have no way to keep track of all the phases of the Phillips screws in the lab bench, or even the little fingers that are grabbing this thing, right? No way. Okay? So that's the usual situation, and this thing here is keeping track of its phases until you destroy it somehow. Destroy those phases. You see, by some measurement, as they say. Okay? So now you might want to say, well, I'd like to see how this rotor behaves relative to something that I am keeping track of the phases. So you get a molecule and you put this rotor on it and you let the rotor turn on that molecule, and now maybe the big molecule and the little molecule, you're keeping track of the phases on that. You're doing quantum mechanics. Okay? But the thing you're going to use to look at it is very classical. And it's forcing this thing to make choices that it doesn't want to make. It has to choose between spin up and spin down. It doesn't want to make that choice. But it will if you force it. But it'll do it randomly. Because the phases it's holding is MC squared, so it's going to be beating between the two possibilities, you see, and every once in a while the symmetry will get just right because some phases in the bench, lab bench, make it right. I mean, I'm talking through my hat at this point, but something like that happens, and so it's been beating back and forth between these two possibilities, and all of a sudden the symmetry breaks just as it's down here beating, you see, and gets stuck. And then the whole thing dies in a measured state. That's a dephasing process, basically. Which is what's got to be behind measuring. What we're doing here is we're drawing a boundary between inside and out. And you do the
semi-classical group theory of the potentials and things like that, and then you put something in there that you're claiming is purely quantum mechanical, at least while you're not looking at it. As soon as you look at it, bam, you're just likely to force us into a death choice. And it'll kill that beautifully balanced wave
Enlightened.
that we got with our group projectors and
Transcendent.
worked so hard on. Yeah. Now becomes something else. And you take your body count and make a cystogram, and you've got, after you've done many things, you start to see, the undulations that correspond to the actual wave function.
Thank you.
You're welcome. It's a